All right, let's solve a heat capacity problem here. And let's solve it in beautiful fuchsia. Can I make it turn out to be something? So here's a problem that you might see. I think it's fairly simple, but it's not bad sometimes to just solve an easy one to gain confidence. So here's our general formula for heating up an object. If you know its heat capacity, remember this is heat as measured in joules. Although technically it doesn't necessarily have to be measured in joules. You could measure it in calories, I guess, or BTUs or whatever, but that would change the units of C, right? Um, and potentially, like if you're doing BTUs, you're probably talking about pounds. I don't really know what a BTU is, but I know it's another unit of heat. And there's a few other ones. But anyway, in SI, this will be in kilograms or grams. This will be the heat capacity, and by the way, that's mass. This will be the heat capacity for the specific material that we're talking about. And this is the change in temperature. And all different objects have their own specific heat capacity. It's a physical property of the object. Okay. So the question that we're asked to solve is, okay, so first, how much energy is required to heat 2 liters of water from 10 to 40 degrees Celsius? And the second part is, if the heating is done on a 1000 watt element, how long will it take? I think your stove is probably more than 1000 watts, but we'll limit it to 1000 watts. So this problem's a little tricky in that it does not give you a heat capacity directly. It expects that you know it. So the heat capacity of water is something that I would suggest is probably worth committing to memory. 4.186 joules per gram per degree. Whether that's Celsius or Kelvin is sort of irrelevant because the degree is the same size. Or if you want, you can also do this. In terms of kilograms, okay? It's a simple conversion to do that. The other thing that you're expected to know is that 1 liter of water should weigh 1 kilogram. Now this is pretty much true. It's actually true at 4 degrees Celsius, but water becomes a little bit less dense as you heat it up, as those molecules get moving. So this is kind of an approximation, but since it doesn't give us any more info on what mass of water we have, it just says 2 liters, we'll make the assumption that it's 1 kilogram. I suppose what we could do is look up how much the water would weigh at 10, but we don't need to go that depth, right? And then the start of this is just solving for Q, right? So Q equals M, well mass is 2 kilograms, right? Because we have 2 liters of water. C we just learned in terms of kilograms is that. Okay. And the temperature change, again, it's a delta T, so it's 40K minus 10K. So that should work out to be 30K in there. And what units will be left in? Well, kilograms are going to cross off. Kelvin will cross off, and we'll just end up with the solution to this, which is 2508. Okay, yeah. Depends what value you use for this, and depending where you look, you might get different values. Um, this seems to be the one that people were using from their own. Okay. Be honest, I'm more interested in whether you understand the use of this rather than how specific you are on these, final significant digits. Okay, it doesn't make all that much difference in the big picture. really we have 3 sig figs here, so we're going to round off to this anyway, right? So this is sort of an insignificant difference. Okay, so what we'll get then is we probably want to do it in terms of kilojoules at this point because that's such a large number. So we would just say probably 251 kilojoules, right? Does that make sense? Okay, and the second part is a time question. So remember or recall that power is a measure of energy usage over time. So how many joules we're using every second, okay? Well, it's telling you the power, and it says 1,000 watts or 1 kilowatt is the strength of this burner, right? So what does 1 kilowatt actually mean? Well, it means that we're using 1,000 joules every second, right? Using 1,000 joules every second. So what we want to know in terms of this scenario is how much time is this going to take? So rearranging the formula, we should get the amount of energy we need is 251 kilojoules, right? Divided by power. In this case, it's 1 kilowatt, or 1, which is the same as saying 1 kilojoules, sorry, per second. Okay, those cross off, the seconds come to the top, and we should end up with 251 seconds. Is that what you guys got? All right, so there we go. How much is that in minutes? What's that? Can you actually, on your stove, heat up 2 liters of water in 4.18 minutes, do you think? Yeah. 2 liters. Okay, so let's say your stove does say 1,000 watts, because you could probably find, like, I mean, the the hot plates around the school are easily kilowatt, but they do take, for 2 liters of water, it would probably take longer than this. Can you think of why it might take longer in practical terms than it does, theoretically? Yeah. Ah, good. Okay, so when you think about it, right, here's your stove top. You got this hot element. You got a pot of water sitting on top of it. Okay. Is there any like shielding to ensure that the heat is going only into the water? Okay, well that's part of it. That's a good point. Okay, for sure. If you put a lid on, that will help to seal in any heat that's getting lost up into the environment. But really, this is a metal tin. It's going to radiate heat out of it, right? So the efficiency becomes an issue. On your stovetop, lots of energy is lost to the environment. Okay? Just on that topic, okay, the way that this is set up is pretty inefficient for boiling water. A better way that we think of is inside an electric kettle. So an electric kettle, right, it plugs into the wall. And what it has inside of it is it has a heating element that actually sits right within the water itself. Okay, so then you're directly heating the water rather than trying to pass it, through this surface. I don't know if kettles tend to be insulated. I don't think they do, but definitely this is a more efficient way of getting energy into the water than this is. Also, there's essentially only this route for direct escape of heated air. The rest of the heat has to escape to the surface. So there you go. Heating element inside. This is how like a hot water tank heater works if you have an electric one. The element is within the water. Obviously, you're going to be careful to insulate it so that you're not putting bare wire in here. This is a specially designed, coated heating element specifically for this purpose. No. No, no. What's inside a heating element is like a really thin, I don't know what the wire's made of. I'm going to say tungsten, but I'm not sure. So a really thin piece of tungsten wire goes through there. It has very high resistance, okay? So you can imagine these are two really thin pieces of wire, okay? And then you're going to coat that with an insulator. A ceramic usually insulator is around that. So you know, most stoves now that I see are the heating elements under a glass surface top, right? But the older style stoves, the kind I grew up with, had this coil element in them, right? And actually, I don't think the coil goes back. I think it loops back underneath. But anyway, um, it's the same principle, right? Like if this were just like electric wire, you would be getting shocked every time you like put your hand near that thing. You know, if you turned it on before it heat it up, right? Or if you touch your pot and you know these are just bare wires, ouch, right? Not a good idea. So this is a high resistance wire within here, but it's coated in an insulated coating, right? To obviously prevent electric current from getting into you. And it's the same concept here, right? The wire that is actually heating up is coated inside a ceramic tree. Okay, so another kind of problem you'll get is a calorimetry problem. So what's calorimetry? Well, is a way, calorimetry is a way of finding an unknown heat capacity. Okay. And we will actually do some crude calorimetry in class with what we have available, but I'll just describe kind of what a calorimeter, a real simple calorimeter is like. Okay. So the kind that we'll use is basically going to be made of an insulated cup. Okay. In a professional model, the insulation is very good, but the principle is the same. Okay. And inside the cup, you're going to put water of a known value. Okay, so known mass of water. You're going to put in a, what do you call this thing? Thermometer. Okay, you're going to put in a thermometer. And, you know, have a starting temperature here. And I'll make up some values. So we have, let's say you have 2 liters of water. Okay, again, just because. And what we're going to do here is we're going to have a hunk of metal. We'll say this is a 200-gram hunk of unknown metal. Let's say we're trying to identify the metal. Well, one physical property that metals have that's different from other metals is what their heat capacity is, right? So if you figure out what the heat capacity is, we could figure out maybe what a metal is. What type of metal this is. Probably the easiest way would be to go by density, but this might be a way to back it up, right? So 200 grams, and let's say that we heat this thing up to 400 degrees Celsius, and let's say that the water is initially at 20 degrees Celsius, okay? So here we have this like really hot hunk of metal. We know it's at 400 degrees because, say, we've put it into an oven and we've measured the oven temperature to be 400 degrees and we've left it in there till it all comes to equilibrium. We know it's 400 degrees. Okay? Then we would take this metal and we would plunge it into our calorimeter. Okay? And the calorimeter is insulated because what we want to have happen is we want the heat that's in here to transfer into the water. Okay? So we know water has a C, or specific heat capacity of 180. And we can use 0, doesn't really matter. Joules, gram, Kelvin. Okay, so we plop that in there and we let it sit for a little bit. And what we should notice is that the temperature of this drops, the temperature of the water goes up. So what's happening here is this. The way we write this out is that the Q, the heat gained by the water, so the heat gained by the water must be equal to the heat lost by the block. Does that make sense? Okay. So let's say after this comes, after we do this, let's say that after a little while we reach a maximum temperature of 25 degrees Celsius. Okay. So we say we time it and we're looking and it gets up to 25 degrees and then it slowly starts to cool off after that as heat is starting to be lost to the environment. Okay. The better insulated our calorimeter is, the better our results will be, right? So we have to understand that the calorimeter will lose some energy as it goes to the environment, right? And the longer it takes, the more it will lose. but we'll just go with these values and see what we get. So let's write that again, just mathematically. So the heat lost by the, or sorry, the heat gained by the water should be equal to the heat lost by the block. Okay. Why do you think that we have to put this negative sign in here? Because we're saying it's equal to, right? So although temperature is not a vector, it can go either in the positive direction or the negative direction, right? So the magnitude is the same, but the direction is different. So we have to put that negative sign in there to indicate that if we want these two things to be equal, then we have to take the loss, turn it into a gain. Do you see what I'm saying? So without this negative, you'll get a negative answer at the end, which obviously you'll realize isn't right, and you'll fix it. Okay. I guess it. Yeah, because I mean we're looking for the heat capacity at the end of the day. So what do? We write some stuff out. So we know from before that for each of these things, this is true. So let's write it down for water. So for water, we have the mass of the water, so sub W, C sub W, delta T sub W, is equal to the mass of the metal, M, C of the metal, block, M, and the delta T of the metal block. Now, which of these values are we actually after? We want heat capacity of the unknown metal. So we want this. So step one is to isolate that. So to rewrite the formula isolating for Cm, we're going to divide these off this side, and we should end up with something that looks like this. The C of the metal should be equal to the mass of water times the heat capacity of water times the temperature change of water divided by the mass of the metal times the temperature change of the metal. Okay, so let's start to fill stuff in. So mass of water should be 2 kgs. Heat capacity of water, 4180. Joules per kilogram per degree. Okay, and the temperature change of water, well, delta is final minus initial, right? So the final temperature is 25 degrees minus 20 degrees. Because it's a delta, we can use K, so this is just the same as saying 5K. We could use degrees over here. It would have been irrelevant to our final answer. The mass of the metal was, what was it? 200 grams. Okay, so 0.2 kgs. And the temperature change was from 400. Oops, sorry, my mistake. Final minus initial. So final temperature was 25 degrees C minus the initial, which was 400 degrees C. So now it's a matter of solving, and we should be able to get the heat capacity of that metal from this equation. So let's try. So by my math, this comes out to be equal to about 560. Now the question is, what units are those? Okay, so let's just see what we have here. So we have K on the top, K on the bottom. So those go away. Okay, so we still have this K here. We have this kilogram and this kilogram. So those go away. So we should be in terms of joules per kilogram Kelvin. So there would be the specific heat capacity of the unknown metal. Is that higher or lower than water's? Way, way lower, okay? Which is exactly what we would expect from a metal, right? You know, and you'll gain more experience in this, but metals tend to have much lower heat capacities than water does, okay? So that's that. Energy to